Hello class, in today's lecture we're gonna replicate the sample problem we did last class in Abaqus. So we're gonna use the commercial software to get the solution of this thin plate problem. So let's recall the problem. So in this problem we have a plate that it's restrained in its left end. So that restraint is represented by applying pins at both the nodal points of the left edge. Then we have pressure at the top edge of 300 psi and a concentrated force of 1,000 pounds on the upper right corner. Then at the lower corner of the right edge, we have a roller. So there's a roller here. It's been discretized into two elements, and the dimensions along the length are of 3 inches and the width 2 inches. It's a 0.5 inch thick plate. The elastic modulus was 30 times 10 to the 6 psi, and the Poisson's ratio was 0.25. And we were interested in finding the unknown nodal displacements and computing the stresses of these two elements. So we're going to replicate this in Abaqus. So I have open CAE here, and I'm going to select with standard explicit model. Then I'm going to follow this tree here under model 1. I'm going to click on parts, and I'm going to say it's a 2D problem. I'm interested in deformed members and of sort of a shell type that will allow me to draw plate system. So here the approximate size, it must be related to the maximum length of the element, so I can get agreed of approximately the same size. So the maximum dimension here was 3 inches, so it's okay if I define somehow around 10. So then I'm going to use the rectangular button here to draw this plate element. And whenever you select this rectangular, it specifies you that you need to select two opposite edges, like here, one corner here and then the other corner like a diagonal from it. So I'm going to specify a 0, 0 point. I can either click on the 0, 0 point in the grid, or I can type it down. You should know by now. And then I'm going to select a length of 3 and a height of 2. And that should give me my rectangle of length 3, height 2, just like here, 3, 2. Okay, so I have my member drawn. You can also use this command to draw it, but you have to specify the 4 corners. So after that, I'll just say done here. And then I'm going to proceed to do define a material. So material. So I'm going to give it a name. Steel. It has pretty much similar properties as steel, so I'm going to say it's steel. So it's going to be elastic problem. All other materials right now here are too complicated for this class, so we're just going to say elasticity and elastic. Young modulus was 30 times 10 to the 6, so you can use the E for times 10 powered, so 30E6, and Poisson ratio 0.25. And isotropic, so I shouldn't touch this, and I should leave it the same. And then you go to assign, define a section. So it's a solid homogeneous, made of a material steel. And here it's where I'm going to define the plane strain or stress thickness. In this case, plane stress. So plane stress of 0.5 inch thickness. And then I'm going to assign this section to my part. So I have assigned that section, and then I can proceed down the tree. So the next step will be to include that part within the assembly. And in here, I just drag and drop different parts. And our models right now are simple, so we always only going to have one part. So you can either mesh it on the part or mesh it on the instance. I prefer to make it independent and mesh it on the instance. And then here I select mesh, and then it's telling me I have to mesh on the assembly. So I'll mesh here within the assembly. So then I go here on the seed command. So this one, it's pretty much gonna tell me how big my elements are gonna be. So since I only want two elements, I'm just gonna define the maximum dimension of my part, which is 3. So it only gives me nodes at the corners. So you see here, it only gave me nodes at the corners. If I had specified something smaller, maybe 1, then I'll get more nodal points, but I don't want more. I just want at the corner, so I'm just gonna say 3. You can also use the edge bias whenever you want to have more elements along an edge, and this is just an example. So if you select this one, and then let's say I just want more elements along those that edge, then here I can say by number and specify, let's say 10 elements along that edge, and I will have 10 elements here, but I don't want 10 elements there. So I'm just gonna use this command here to erase it. And then I'm just gonna give my global seeding assignment. Then I'm gonna define what element do I want. And in 2D, we can have quads. We can have a combination of quad and triangle for difficult geometries, or we can just have triangles. So I'm just gonna say triangles and structure. And structure just gives you a very organized mesh. Whenever you have a free mesh, you're gonna have a messy mesh. So structure, and then I'm gonna say assign element type for this whole region here. And it has to be a linear element, triangular, 3-noded, plane stress triangle. So the default was okay, so I don't have to modify it. So linear, plane stress, and triangular. So can you have a quadratic triangle? Yes. So see what happens when I select quadratic. So it's going to be a 6-noded element. Still a triangle, but 6-noded. But I don't want a triangular right now. We are still on linear 2D elements, so I'm just going to say linear. So linear, plane stress, and 3-noded. So okay, and then I just mesh here. And I have the two triangles similar to what I have here. Now, because Abaqus uses its own numbering of nodes and elements, I might not get the same numbering of elements and node, but remember the solution should be independent of the node numbering and also of the origin location. So let's see what happens. So here, assembly display options. I want to see displays the mesh, show node labels, show element labels. So the 1, it's at the origin. So now here my 1 is the 0, 0. This is my 2, that is my 3, and that's my 4. This is my element 1, and this is my upper element 2. So I should get the same solution regardless that I have different node numbering. The next step would be to define a step. So here I go to step. I need a step in which I can apply the loads. So it's going to be a static problem because the solution don't depend on time. And I say continue. This I shouldn't alter because they don't make a difference when the problem is static. So I'll just say okay. Then I go here and I define the boundary conditions. The boundary conditions are there. You can either define it on the initial or step 1. I'll just define it in the initial. And remember, we have the left edge, it's pinned. So you have here 2 options. And you can either select the nodes and apply U1, U2 equals 0, or you can select the whole edge. And I prefer selecting the whole edge. Let me delete this one. Just because it gives you the impression that the whole edge it's pinned, as it should be in the real problem. But in reality, it's only applying boundary conditions to that node because we can only apply boundary conditions to the discretized nodes. But For visualization purposes, I like to select the whole edge, but it won't change the answer. Then I applied the loads, and the loads I like to apply them on the step. And then the concentrated force was in this node here, and it was minus 1,000 pounds. And it's in the 2 direction. And then we had a pressure, so we had to apply another load, pressure. And that pressure is on this top edge. And the default in this Abaqus, at least in the student version, is that positive, it's going into the surface. So that's why I say 300. So it's not related to the direction, but if either into the surface or out of the surface. And this is confirmed by the arrows. So you see here, it's into the surface, it's positive, so it's 300. So let's say I had changed this to minus 300, and it goes out of the surface. So default, if it's into the surface, is 300, which is opposite to what we do when we solve it by hand. In that case, the Py was minus 300, but this is just because that's Abaqus convention. Okay, so I have the 300 PSI, the 1,000 pounds. This one is a roller. I'm missing that one as a roller, so I have to apply that boundary condition. So now I just select for this one, this boundary condition only, it's for that node. So only that point is going to be U2 equals 0. So that's U2 equals 0. And then I have done everything to solve the problem. Let me see if I get the outputs that I want. So in my field outputs, the defaults are stresses, strains, displacements, forces. So that's more than enough that what I'm looking for, because I'm looking for displacement stresses on stresses. So let's just go down and create a job for that model 1. And let's call it replicate in class problem. And then just submit the job. And here we're going to get an indication if the input was done correctly, and it was completed successfully. And it actually performed the analysis successfully, so we have the results available now. And these are our results. So I just went here. The default is that it first gives me the misses stress, which is a stress result based on combining the results of all the stresses. We'll get to misses stress in a later class, but for now, let's just start looking at the displacements. So these are the displacements. So let's look at U1. So as we were expecting, the node here should displace more, and it goes down. And then this one, it's pinned, so it doesn't move. And then this displaces like this. This node cannot move in the y direction. It doesn't. And it actually would help if I put here the original versus the later, this deformed section. So here. So this is the original. Then you see this node move here. This node moved along the x, but not in y. So it's fine. So the displacement look accurate. Now look that you get counter results within when you see the displacement field, and that is accurate. The displacement should change along x and y. Let's recall a previous lecture in which we defined what would be the displacements within the element once you know the displacements in the 3 nodes of that element. So let's go to a previous class lecture, and I think that should be somewhere here. So yes, so here, so look at this. So let's say we wanted the displacements within U, the displacements U, which represent U1 in this case. So all we have to do is evaluate N1 at that location xy, multiply times U1 of that element, the nodal displacement at this point, plus N2 evaluated at that point xy, multiply times U2, plus N3 evaluated at that point xy, multiply times U3. So your U, it's a function of x and y. Your B should also be a function of x and y, but it's only dependent on the displacements in the y direction. So bxy, or u2 in Abaqus, equals n1 evaluated xy. So any point xy within that element times v1 plus n2 xy v2 and so on. So these are the equations to get that u. And that's what we get. So we should see varying displacements x in the x direction and varying displacements in the y direction. So our results match our theory. Now, what about the strains? So we said the triangular elements are considered a constant strain triangle, and you can see it here. So you get one strain result for the whole element and one strain result for this other element. So this is the element 1, element 2. And let's see, so this is the strain in the x direction. So again, one strain value, one strain value. If we look at the stresses in the x direction, one stress value, one stress value. And we can see the stresses in the 2 direction, one stress, and then shear stresses, which also one value. So consistent to our results. Now, stress 3,3 should be 0 because it's a plane stress element and the stress should be 0. Okay, now we look at see if we get the same results. So let's start with so let's output the displacements. So let's see if we get the same results are in our problem. So we're gonna go here, we're gonna look at unique nodal. Output the displacements to our file. Let me call this file replicate results.txt, and by default it's going to go to the text folder, to the temp folder, and let me go find it now here. So these are the results. So remember, we're not going to get the same node number, but we should get the same results. So this is, first let's look at node 1, which was the origin. So it's a numerical problem, so it should be 0, 0, but numerical, it's close to 0, according to the solver that Abaqus had. So this, we can just say these are zeros. And then let's look at the displacement in the x direction of that second node that has a roller. In our case, that was our node 1. And then we can scroll down here to our displacement, and here u1, and it's actually 0.2337, and this is what we got, 0.2337. If you go here, this is -4, and then the other ones are -6, but if we just move twice the decimal place, we get the same results. Now, what about the other node that can deform in both directions? So we got in the x 10.6947 and then -90.83 E6. So let's look here our results, and yes, they are pretty much the same, 0.1069 and then -0.984, and again we can see the other one 0.2337, and then the rest of them are just zeros. The -36 are all zeros. So now what about the stress results? So again, we look at the stress so we can report them, report field output. Now in this case, you can report them at the integration points, although as you can see, the triangular element doesn't need integration points because we saw from previous classes that it just multiplies the b times the d times the b, and we don't need to integrate. So we don't really have integration points for this linear triangular element, and that's why we're getting constant results within the stresses, constant results within the element. But let's just output it, and we're going to output S11, S22, and S12. Yeah, let me get rid of this ones, of the U's, and this is going to go to the same file. So let me open it again. It's gonna be below here. So the first element, which actually it's also our first element, we get this result. So let me just put it here, minus 114. Okay, so let me bring the results here. Stress element 1. So you see minus 114.1, minus 139.1, and minus 676. And then for this one, we get 114, 28.52, and minus 36.35. So it's very important to point out that the stresses and the strains are constant. So they don't change within X and Y of an element, but the displacements do change within the X and Y of the element. So this is the lecture for today. Please replicate this problem in Abaqus by yourself. And before we finish today's class, I just realized that, yes, I'm missing a 1 here. So that's why this one was a different decimal digit here. So there should be another 1 here. So this is 1,391.1. and it will match. And then if you do the calculation here, that should have given you 1,391.1. So just to verify that our results match.